All right, today we are cracking open the black box of AI memory to look at a genuine scientific mystery. Get this. Researchers set a trap for an AI, a puzzle it was specifically designed to fail, and it solved it anyway. So let's dive in and figure out what is really going on inside these things.
We think we have a pretty good handle on how these models store facts. But it turns out this one single experiment just throws all of our most basic assumptions right out the window. It reveals something startlingly complex happening inside the machine's mind. So the big question is, how does an AI actually remember things?
Okay, so meet the path star maze. Now, it's not a physical maze, of course, but a web of connections just stored as pure data. Think of it like a family tree with a central root and dozens of these long branching paths. And here's the kicker. This structure was specifically, intentionally designed to break an AI's ability to reason its way from a start point to an end point. And yet, the AI solved it. Wild.
The task itself sounds pretty straightforward, right? First, the AI has to memorize every single connection in the maze, one link at a time. It's kind of like learning every single street turn in a massive, sprawling city. Then you're just given an endpoint, say a single leaf on one of those long branches, and you ask it to trace the entire path all the way back to the root. Simple to describe, sure, but for an AI, this should have been next to impossible.
And this is the real head-scratcher. The model didn't just succeed, it succeeded with incredible accuracy. We're talking about mazes with thousands of nodes and paths that were 10 steps long. I mean, this result is a total paradox. It just completely defies what we thought we knew about how these models store and recall simple facts. So seriously, how did it pull it off?
Okay, so to really get why this is so bizarre, we need to look at our old theory of AI memory. Let's call this suspect number 1 in our little investigation, the simple lookup table.
So this is what's known as associative memory, and honestly, it's the most intuitive way to think about it. The AI just stores pairs of facts. It learns that point A is connected to point B, and then completely separately, it learns that point B is connected to point C. It's basically a giant brute force contact list that has absolutely no sense of the bigger picture.
And this really shows you what that looks like. Each point is just kind of floating out there in space, only aware of its direct immediate neighbors. There's no map here, no structure, no sense of where anything is in the grand scheme of things. It's just a big jumble of local connections.
And that right there is exactly why this associative memory idea should have failed. I mean, to find a 10-step path, the AI would have to do 10 separate lookups, one after the other, with zero guidance. That's what we call a compositional reasoning task. And for these models, that's not just hard, it's exponentially difficult to learn. The odds are just astronomically against it. So the crucial takeaway here is, this can't be what the AI is doing. No way.
So if the AI isn't using a simple lookup table, what on earth is it doing? Well, this leads us to a pretty radical new theory. It's not just storing facts, it's actually building a map.
Researchers have a name for this, geometric memory. So instead of that messy, disorganized list of connections, the AI arranges all the points from the maze into a coherent structure, like a mental map in a virtual space. And on this map, the distance and the position between points actually tells you their relationship, even if they're not directly connected.
And wow, this just brilliantly shows the difference. I mean, look at this structure. The AI has organized all those points into these clean, logical shapes. All of a sudden, what was an impossibly hard reasoning problem becomes a simple navigation task. Finding the path isn't about chaining a dozen lookups anymore. It's literally just looking at the map and seeing the route. It's a game changer.
Okay, this table really lays it all out, and the contrast is just stark. You've got associative memory, which is basically a local lookup table, versus geometric memory, which is a global map. One makes reasoning exponentially hard, the other makes it, well, an easy navigation task. But the most important difference, the one you really need to see, is in that last row. Associative memory only stores facts it has already seen. Geometric memory actually synthesizes new relationships. It figures out the bigger picture all on its own.
So, okay, we have two competing theories. How do we know for sure which one is the right one? Well, this is the cool part. The researchers actually found a way to look inside the AI's memory and see the structure for themselves.
And honestly, the evidence is stunning. On the left, you see what we thought we'd find, that messy, disorganized cloud of points you'd get with associative memory. But on the right, that's what the researchers actually found inside the model, a beautifully structured geometric map.
The AI didn't just memorize the facts of the maze, it actually understood its shape.
This image right here, this is the smoking gun. What you're looking at is a visualization of the AI's actual memory. Each colored dot is a single point in the maze, and the colors tell you which path they belong to. And I mean, you can see it clear as day. It's not random at all. The AI has grouped all the points from the same path into these perfect, distinct clusters. There's no other way to say it. It built a map.
Okay, so we know what the AI is doing. It's building this incredible geometric map. But that just leads to an even deeper and maybe even more confusing question. Why? Why would it do this?
This is what the paper actually calls the memorization puzzle. See, building that elegant, complex map is way harder for the AI than just making a simple lookup list. In fact, the research shows that just learning a simple list is actually faster and easier for the AI, especially at first. So, why go through all that extra trouble? And what's so fascinating here is that all the obvious answers just don't work. First off, the map isn't a more compact or efficient way to store the data. Second, the model had plenty of power to just use a simple lookup table, so it wasn't forced to do this. And the most bizarre part of all, this happens even when the AI is only asked to memorize facts without any complex reasoning task whatsoever. It chooses to do things the hard way, all on its own.
So, the answer to this whole puzzle points to something really fundamental about how these networks learn. And believe me, it has massive implications for the future of AI.
The best theory the researchers have right now is a phenomenon called spectral bias. Now, I know that sounds super technical and deep, but the core idea is actually pretty intuitive.
Just think of it as an inherent tendency, like a preference that's baked right into the AI's learning process. It's not just trying to get the right answers, it has this built-in drive to find the deepest, most fundamental patterns in the data it sees. It's kind of like a musician listening to a sea of noise and just naturally finding the harmony in it. It wants to find the underlying structure.
So, why does any of this matter? Well, the implications are just huge. For one, it could be a source of real creativity. This map-making could help AI discover novel connections between scattered bits of information. But there are challenges. This hidden organization can make it much harder to edit or unlearn a specific fact because everything is tangled together. It might even be a source of hallucinations, causing the AI to invent these illusory correlations that aren't really there. The good news is, now that we know this is happening, we can actually try to build AIs with even more powerful geometric memory.
At the end of the day, this discovery really changes how we have to think about AI memory. It's not just some passive database of facts. It's an active map maker, constantly trying to chart the territory of the data we give it. And that leaves us with a pretty profound question to chew on. If an AI builds its own map of a simple maze, what new continents of knowledge will it discover when we give it a map of our entire world?